Welcome to the next section, Clustering Your Data, Unsupervised Learning for Predictive Analytics. Now, we move on to the first video of this section that deals with using K-means for predictive analytics. Unsupervised learning is a type of ML algorithm used for grouping related data objects and finding hidden patterns by inferencing from unlabeled datasets, that is, a training set consisting of input data without labels. Let's see a real-life example. Suppose you have a large collection of not pirated totally legal MP3s in a crowded and massive folder on your hard drive. Now, what if you can build a predictive model that helps automatically group together similar songs and organize them into your favorite categories, such as country, rap, and rock? This is an act of assigning an item to a group so that an MP3 is added to the respective playlist in an unsupervised way. Unfortunately, we don't always have that extravagance when we collect data in the real world. For example, suppose we'd like to divide a huge collection of music into interesting playlists. How can we possibly group together songs if we don't have direct access to their metadata? One possible approach is a mixture of various ML techniques, but clustering is often at the heart of the solution. In other words, the main objective of the unsupervised learning algorithms is to explore the unknown hidden patterns in the input data that are unlabeled. Unsupervised learning, however, also comprehends other techniques to explain the key features of the data in an exploratory way toward finding the hidden patterns. To overcome this challenge, clustering techniques are used widely to group unlabeled data points based on certain similarity measures in an unsupervised way. In clustering task, an algorithm groups related features into categories by analyzing similarities between input examples where similar features are clustered and marked using circles. Clustering uses include, but are not limited to, anomaly detection for suspicious pattern finding in an unsupervised, text categorization for finding useful patterns in the tests for NLP, social network analysis for finding coherent groups, data center computing clusters for finding a way of putting related computers together, real estate data analysis for identifying neighborhoods based on similar features. Clustering analysis is about dividing data samples or data points and putting them into corresponding homogeneous classes or clusters. Thus, a trivial definition of clustering can be thought of as the process of organizing objects into groups whose members are similar in some way, as shown in this figure. A cluster is therefore a collection of objects that have a similarity between them and are dissimilar to the objects belonging to other clusters. If a collection of objects is provided, clustering algorithms puts these objects into groups based on similarity. For example, a clustering algorithm such as Kmeans locates the centroid of the groups of data points. However, to make clustering accurate and effective, the algorithm evaluates the distance between each point from the centroid of the cluster. Eventually, the goal of clustering is to determine intrinsic grouping in a set of unlabeled data. Clustering is a process of intelligently categorizing items in your data set. The overall idea is that two items in the same cluster are closer to each other than items that belong to separate clusters. This is a general definition, leaving the interpretation of closeness open. For example, perhaps cheetahs and leopards belong to the same cluster, whereas elephants belong to another when closeness is measured by the similarity of two species in the hierarchy of biological classification. Now, let's use K-means for predictive analytics. K-means is a clustering algorithm that tries to cluster related data points together. However, we should know its working principle and mathematical operations. Suppose we have n data points, where then x base to I equals to 1 to n that need to be partitioned into k clusters. Now that the target here is to assign a cluster to each data point, K-means aims to find the positions mu base to I, where I is equal to 1 till k of the clusters that minimize the distance from the data points to the cluster. Mathematically, the K-means algorithm tries to achieve the goal by solving an equation, that is, an optimization problem. Considering these distance measuring algorithms, it is clear that the Euclidean distance algorithm would be the most appropriate to solve our purpose of distance calculation in the K-means algorithm. The centroids are then updated to be the centers of all the points assigned to it in that iteration. This repeats until there is a minimal charge in the centers. In short, the K-means algorithm is an iterative algorithm and works in two steps. The first is cluster assignment step. K-means goes through each of the n data points in the dataset that is assigned to a cluster closest to the K-centroids. Then the least distant one is picked. The next step is update step. For each cluster, a new centroid is calculated for all the data points in the cluster. This is the flowchart overall workflow of K-means. Now we will see using K-means for predicting neighborhoods. Now, to show an example of clustering using K-means, we will use the Saratoga NY Homes dataset downloaded from this website as an unsupervised learning technique. The dataset contains several features of the houses located in the suburb of the New York City. For example, price, lot size, waterfront, age, land value, new construct, central air, fuel type, heat type, sewer type, living area, percentage college, bedrooms, fireplaces, bathrooms, and the number of rooms. The target of this clustering technique is to show an exploratory analysis based on the features of each house in the city for finding possible neighborhoods of the house located in the same area. Before performing the feature extraction, we will load and parse the Saratoga NY Homes dataset. However, we will look at this example with step-by-step source codes for better understanding. First, we define these two lines of ignore the warnings. Next, we will load required libraries and packages. We need some built-in Python libraries such as OS, Random, NumPy, and Pandas for data manipulation, PCA for dimensionality reduction, matplotlib for plotting, and of course, TensorFlow. Next, we will load, parse, and prepare a training set. Here, the first line is used to ensure the reproducibility of the result. The second line basically reads the dataset from your location and converts it into the Pandas data frame. We will print the data frame. We will find the data frame containing headers and data like this. Well, we've managed to prepare the dataset. Now, the next task is to conceptualize our K-means and define a function or class for it. Next, we will implement K-means. This is the source code of K-means, which is simple in a TensorFlow way. This code contains all the steps required to develop the K-means model, including the distance-based centroid calculation, centroid update, and training parameters required. Now, we will cluster the houses. Now, this function can be invoked with real values. For example, our housing dataset. Since there are many houses with their respective features, it would be difficult to plot the clusters along with all the properties. This is the principal component analysis. Well, now we're all set. It would be even better to visualize the clusters using a plot. For that, we will execute these lines of code with 3D projection. Here, we can see that most houses fall in 0 to 1 lakh range. The second highest houses fall in the range of 1 lakh to 2 lakh. However, it's really difficult to separate them. Moreover, the predefined clusters that we used is 10, which might not be the most optimal one. Therefore, we need to tune this parameter. We have redesigned our K-means considering the WCSS value computation using these lines of code. Now, we will train the K-means model for different K values that are a number of predefined clusters. We will start K is equal to 210. Now, let's discuss how we can take advantage of the elbow method for determining the number of clusters. We calculated the cost function WCSS as a function of a number of clusters for the Kmeans algorithm applied to home data based on all the features using these lines of code. For better visualization, we will minimize the size. We will try to reuse this lesson in upcoming examples using Kmeans too. Now, it can be observed that a big drop occurs when k is equal to 5. Therefore, we chose the number of clusters to be 5. Basically, this is the one after the last big drop. This means that the optimal number of cluster for our dataset that we need to set before we start training the K-means model is 5.